Welcome to Module C, Lecture 4. In this lecture, we shall continue our discussion about the stepwise approach of multilevel regression analysis and shall take a few more examples. In the last lecture, initially we talked about two approaches of doing the trip generation analysis. The multiple regression analysis and also the cross classification or category analysis. Then we started more discussion about regression analysis, how to develop regression equations and what we try to do in regression model, and then went to talk about the steps one by one. We said the first step is to try to detect nonlinearities, and if we find nonlinearities between x and y, between any independent and dependent variable, then we make suitable transformation of variables to make the relationship linear. Then second is develop the correlation matrix which any computer program can give, and then try to investigate if the correlation independent variable, each independent variable and dependent variable have high statistical association. In fact, we want that. So, if we get strong statistical association, they are our strong candidate. So, that means for modeling y, we can use expressing y, we can use those x values. The weak one alone cannot be used. And also we wanted to see if independent variables, some of the independent variables are really collinear. So, each pair of variable, what is the correlation coefficient that we wanted to check, and if the correlation coefficient between two variable is high, that simply indicates that they are collinear. Collinear means they are not independent variable. So, by default our assumption is that all x are independent variable, but if two variables are collinear, then they are not independent, because one variable can be expressed as a function of the other variable. So, we do not want and we cannot include collinear variables in the same model. Then we said that given a hypothetical example of a correlation matrix, how we can logically select the models. And there I said that we first tried to find out who are our strongest player. In that example, if you go, you will find that x 1 and y is a potential specification, is a potential combination, because x 1 and y very strong association. Similarly, x 3 and y strong association. So, we also took that. We took one model as y equal to a plus b x 1. We took another model y equal to a plus b x 3, fine. Then logically, if two are so strong, can we put them together? Then our model also will be very strong. Yes, we should try to do that. So, we tried to put x 1 and x 3 together, and luckily in this case x 1 and x 3 are not collinear. So, there is no problem in putting them together. So, we put them together. Then we found x 4 is also not x 1 x 4 not collinear, x 3 x 4 also not collinear. So, we could easily add also x 4 and try to develop another model and try to see if that gives us better goodness of fit. What was left out? Theoretically some more combinations, yes, but you know that when x1 and x2 are two strong players, we try with x1 alone, we try x2 alone, x1 and x3 alone, then x1 and x3 combination, then also want to include x4, but x5 we cannot include with x3 because x3 and x5 are collinear. So, then I could theoretically try another model where only I have x2, x4 and x5 omitting x3, but then whom you are putting in the sideline? You are putting a very strong variable x3 and bringing x5 in lieu of that, right. One can try, but most cases I will say based on my experience of modeling that you are unlikely to probably get that as a finally the best model. But of course, there is no harm, you can always try a few more combinations. So, with these 4, let us take this 4, or if you wish maybe let us take for the sake of argument another 2 or 3 variables models also we could consider. Fine, we could consider that, nobody stops you, you can explore, in whenever you will actually develop a model, you can explore even more possibilities. But here let us take for this example, we go ahead now with this 4 model specification. So, what is the further step? After specification, it is the calibration. So, let us go for that. So, we now go for calibration. So, we estimate the parameters of each of the potential equations that again computer will give you, Excel can give you, many other software which are commonly used can give you. So, I will again not tell you how to estimate the equation, because that most computer program will be able to do it. Estimation technique and other things you learn. I will again discuss something which the computer will not be able to do, that you have to do as a planner or as a modeler. Decision making again based on the values given. So, how to then select a model? You feed that thing, you decide the model specification, you have a set of data. So, in each case the coefficient estimates go to the previous equation, first case A and B, second case A and B, third case A, B1, B2 and the fourth case A, B1, B2 and B3. All these coefficient estimates will be available to you. Now, decision has to be taken by you which model you are going to finally accept. So, what we all need to check? We need to actually check maybe these 4 aspects. First, what is the magnitude of the R square? Okay, that we need to check. Second, we need to check, do the partial regression coefficients have the correct sign, very important, logical sign. If I know if x increases, y should also increase. Say for example, if a type of employment increases, the number of trips attracted should increase, cannot decrease. Everything else remains same, it cannot decrease. So, population increases, number of trip production should increase, it cannot decrease. So, the logical sign, correct sign. And second, are their magnitudes reasonable? Magnitudes sometimes get distorted. So, if you have used collinear variable without checking, if collinear variables are inserted in a model, the coefficients get distorted, because it is getting distributed in 2 variables. Same thing getting distributed in 2 variables, because they are collinear. So, this is again important that you should check the, are you getting a logical value? Per household trip rate, okay, you know wherever you are working, Indian cities, this kind of cities, medium mid-sized cities or big metros or this, in what range they vary normally. So, I should not get something totally upside down, a completely different value, it is not possible. So, you know that you may not know the exact value, of course, none of us, we may not know, but we should give a value which sounds logically explainable, right. You should be able to explain it logically. So, the correct sign and logical magnitude. Third, are the partial regression coefficients statistically significant? Take any model specification, give any data set, it will give you some coefficient estimate. But does it mean we are going to use that? No. We need to check whether these coefficient estimates are statistically significant. What does it mean? You get a value, but the value alone does not tell you whether they are statistically significant. Why? Because the value of the coefficient depends on the unit of the variable. Say for example, just I am giving you an example. If I take rupee as my unit, not directly related to this, but still it is a good example. Let us say rupee, I express my cost in rupee. I may give a big coefficient into rupee. Rupee is my variable, let us say x. So, a big coefficient value a into x. You take the same rupee in express it in thousands, the coefficient value will be small. You express rupee in crore or million, billion, you may get a few decimal also, a very small value. So, how big or small that value, that does not tell you anything. What is important is that coefficient estimate statistically significantly different from 0. If the coefficient estimate is statistically significantly different from 0, then it is actually contributing to explain you why. And if it is not statistically significantly different from 0, then that coefficient and 0 statistically are not different in a way. So, inclusion of that does not make sense. Whatever remaining thing we interpret, that variable you have included forcibly, it does not contribute. It is a garbage. So, we must check that. Fourth, is the magnitude of A reasonable? What is A? I hinted in my previous lecture. A is the unexplained component, constant. It is quite okay if you get a component which is the unexplained component, there is nothing wrong. But if you find that my constant value is a very high value, that means I am not able to, with my combination of variables, I am not able to explain the variation of y adequately. Lot of portion is unexplained. So, given everything else same, if I am getting two alternative model, everything else is same, but one case I have a high a value, another case a low a value, obviously I will prefer the low model with a low value of a, low unexplained value or constant. So, all these are to be checked. Most students, they forget all this, only select high R square, sir I got high R square means my model is very good. No, you have to actually check all these aspects, and these are extremely important, and a computer program will not give you decision, it is you who have to take a call and then select and tell which model is the best for the given data or for the given context. Let us take an example to move forward. The four models what we selected, let us assume that for a given data when we fit the model, we get these results to carry forward our discussion. The models we selected for the given data, we put those models and whatever computer generated are given here. Look at this equation, y equal to 894.5 plus 0.66a, y equal to 444.39 plus 1.045 x 3, then y equal to 180.4 plus 0.38 x 1 plus 0.65 x 3, and the last one y equal to 957.55 plus 0.35 x 1 plus 0.55 x 3 minus 32.65 x 4. Okay. And along with that, I have given standard error of estimate, R square value and t value. So all are given. Standard error of estimate also you can check. Okay. Obviously, even given everything else same, all other parameter, we would actually select a model where the SSE is lower, standard error of estimate is lower. So, now the decision to be taken, which model among these four should be accepted. Let us look at this based on R square, 0.68, 0.74 for B, 0.85 for C and 0.92 for D. So, in terms of R square, the best one is model D. But then let us check other points. As I said, R square is not everything. R square is one aspect which should be checked. And from the point of view of R square, D is my selection. But can I go ahead with that? Let us see. First thing, immediately I can see in this slide, we need to check if the coefficient estimates are statistically significant. I can clearly see the t value of x 4 in model D is 1.27, which is not statistically significant even at 90% confidence level. Of course, I have indicated here the t value depends on the confidence level. Normally, we take 95% confidence level. Some cases you can even take 90% confidence level, that is also fine. And planning purpose, we normally do not expect this in a 0.92 we have shown, because this is an hypothetical example. I have taken the freedom to put a high R square value, but this much high R square value unlikely to be obtained in any planning studies, right. Even a lower R square is fine. But here what you find, this t value 1.27, it is not statistically significant, right. I have indicated here, if you want to calculate t value, you have to see the confidence level, you have to see what is the degrees of freedom, which depends on the number of variables considered in the equation, and then what is the estimated t value after calibration of the model. That estimated t value has to be greater than the tabulated t value. So, generally I would say even in 90% confidence level, it should be around 1.64, but I find it is even lesser than that, around 1.6, 1.64, that around that it should vary, expected to be around that. But here it is 1.27. So, 1.27 is definitely not statistically significantly different from 0 at 90% confidence level. So, this is a forced inclusion, does not help. So, how can I, even if I get high R square, it does not make sense. Second, let us look at the sign. Sign has come as negative. What is x 4? X 4 is the distance from CVD, yes, then it is logical. Distance from CVD, the more the distance from CVD, the trip generation will reduce. We are trying to say peak hour trip produced. Peak hour trip produced may reduce with the distance. So, with population it should be positive, with number of household it should be positive, with vehicle ownership it should be positive, but with income it should be positive, but with distance from CVD it is likely to be negative, because distance increases. So, number of trip production will reduce. So, its negative sign is logical. So, what I found here, the t value coefficient estimates is problematic. So, maybe I will not use this model. Among other models, 0.85, yeah, t values are fine, signs are also fine. If I go back, all cases t values are fine, the signs are also fine, but look at this, the unexplained component A, B and C. Unexplained component here is the highest, 900 vis-a-vis nearly half of that, and compared to B, A is again further reduced, even less than half of that. So, if I have to select, I would probably reject A because of the high, unexplained component, unusually high. Now, between B and C, so A is rejected because of the high, everything else is fine. So, I have to compare it based on other parameters. So, I found that A is basically high, unexplained component or constant as compared to other two. So, we will reject. Then B and C. Also, A has got the least R square value, that is also one more reason. So, the model is not good. So, the R square is also getting reflecting that. So, if I have got a model with 0.85 or 0.74 and then with a higher unexplained component and with a lower R square value, why should I accept A? So, obviously, A gets eliminated. Now, I have B and C. B and C, sign fine, coefficient values logical, statistically significant estimates, both cases it is they are statistically significant. Here it is 444.39 and there it is 180.4, but obviously I also find that the R square is more. So, if I have not missed any point as I am looking it now here in the screen, then the choice should be actually model C. That means, I am using population and vehicle ownership. Okay? So, vehicle ownership data or vehicle data. So, that way probably we should take a final call and we get a better model here. 0.85 is the R square as compared to 0.74. So, obviously, and the standard error of estimate is also low. yes, it is lower than even what we got from B, and R square is also improved. So, we select that. Now, let us take another example. These two equations are giving. These are again hypothetical example, because I quickly want to convey to you a few other things. Let us take a model. We are trying to do now peak hour trip attraction. One case I gave you 61.5 plus 0.93 x 1 is total employment, and here I get standard error 208, R square 0.9 and t value 42. 42 is very high. So, obviously, it is statistically significant, there is no doubt about that. And second equation I get 25.8 plus 0.89 x 2 plus 1.29 x 3, R square is 0.91, okay, it is also very high, even 0.01 value higher than the previous one, and t values are 51 and 17, that is fine. Now, one thing I should tell, and you should know probably, the t value we are only worried whether it is statistically significant or not. Now, once it is statistically significant, whether the r value is 10 or r value is 50, that is we are not going to consider that, because it does not make sense to consider. Both cases it is statistically significant. So, we only want to make sure that it is statistically significant, right. So, 51 and 17 both are square values are very high, both are acceptable at 95% level. So, which model to be selected? Both are very competitive model, you see. It is very interesting example, because both models are competitive, both are good, both cases are square as same, statistically significant coefficient estimate, and if you say peak hour trips attracted, number of trips getting attracted in peak hour, 61, 62 is higher than obviously 25 or 26 values, but 60 is also not a high value. In a zone, how many trips are getting attracted? 50, 60 is unexplained number, is nothing actually. Both are low value, not high. So, which one to select? Here, look at this part, very competitive, highly comparable models. So, any one you can select, but then finally, if I have to select one, I will go now beyond all the checks what I have said to you so far, because all those checks are giving me a tie, but I have to do something to break the tie. So, I bring another consideration now. You see, what is x 1? Total employment. What is x 2 and x 3? Are the two categories of employment. Here first one variable, second one two variables. So, normally two variables are more parameter richer than one variable. That model will be more parameter richer, but by adding more parameter or variable, I am not able to get a significantly better model, because 0.90 and 0.91 R square no difference, 61 and 25 constant values again no difference. So, there is actually no difference. So, then why I consider more variables in a model? Because it not just developing the model now, but you are developing the model for the future. So, you have to predict it, apply it for the future, and if I am using parameter richer model, then I have to do forecast of these each variables accurately. Why I should additional efforts? Because if I say you predict one variable and you predict 5 variables, and that too you look at this, total employment prediction is likely to be much easier than the predictions of category wise employment. Like prediction of population for India and prediction of population for a state vis-a-vis prediction of population or forecast of population for a district, where we are going to be more, where the error is likely to be more. Think carefully. So, the same spirit we are bringing, because there is no significant gain by putting more variables and looking at the variables, that first case it is the total employment, the second case there are two different categories of employment. If I am not getting any significantly better model, then I must use or accept a model which I can apply easily in the future. So, I am now thinking beyond all the checks that in the future I have to apply. I have to predict my or forecast my independent variable. So, which one will be easy for me to apply? So, based on that I will select the first model. So, with this, that is what I explained here. The standard errors of estimate of both the models are almost close. R square values of both the models are very high and close. Two models, all variables are statistically significant. Magnitude and sign of the coefficients of both models are reasonable, and altogether there is no big difference between the constant values of both the models. So, in this case simple model with a single variable is chosen, but if I would have got by inclusion of more variable a better model, significantly better, my R square jumps from 0.8 to 0.9 or 0.7 to 0.78 or 0.75, I would have used that parameter richer model. So, that is what. So, we discussed here stepwise approach. Once you have the estimated parameters, then how to select the model based on magnitude of R square, standard error, looking at the t value or statistical significance of the coefficient estimates, looking at the sign and magnitude of the constant and the sign and magnitude of the coefficients, and then also give some examples to explain you different aspects. And once you have a tie of all these, every case it is giving good from all this perspective, then what to think? Then think of the applicability. Okay. So, with this we close here, we continue in the next lecture. Thank you so much.